Hi everybody, welcome back. This is the final video in Unit 6. I think it's Lesson 9, if my memory serves me correctly. And we just have to wrap up these two little sections of notes that we have. We're talking about intermolecular forces of attractions, or IMFs. Those are attractions between whole molecules. And we've dealt with dipole-dipole, which are attractions between polar molecules. And we've dealt with hydrogen bonds, which are attractions between molecules that have H and O, F, or N. So the remaining two are molecule ion attractions and van der Waals forces. Molecule ion attractions occur when you have an ionic compound, right? A metal and a nonmetal, like sodium chloride, where your metal's positive and your nonmetal's negative. When you take an ionic compound like that and you dissolve it in water, okay? And this works because water's polar and has the partial charges. So remember, in water, oxygen has the kind of negative charge and hydrogen has the kind of positive charge. What happens is that water pulls the ions apart. And there is an attraction then between the water molecule and the ions. And these are called molecule ion attractions. I want to show you how that works, and then we'll fill the rest of this in. So I have a little animation here, which I cannot click from my board. Well, I'll put that back up in just a minute.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride dissolving in water on a microscopic scale.
I wish everything had a zoom button. The zoom button is like putting on your Miss Frizzle glasses. So what we're going to do is take you down to the ionic level here, right? The subatomic. So a microscope can't see this. This is so small that a microscope can't even zoom in enough. But if we could look at what just happened and the reason salt dissolved, we would see this.
Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
Okay, so this big, chunky looking square cube thing is salt, NaCl. It's when you look at a grain of salt, like a little salt crystal, that's what you're looking at. That's what it's composed of. Lots of Na pluses, which are the orange guys, and lots of Cl minuses, which are the green guys, okay? When you put water in them, since water has partial charges, or you put them in water, oxygen's negative. So oxygen cozies up to the orange guys and pulls the positive ions towards it. And hydrogen, which is positively charged in water, cozies up to the negative and pulls them towards it. And so there's an attraction between the water molecules and these ions in solution. Okay, and those attractions are known as molecule ion. You have to know which way the water molecule orientates itself when it attracts itself to the ions. So I want you to draw this because I think it's important that you draw it. And we'll draw it kind of at the bottom. Okay? If you have Na+, since opposites attract, the negative part of water will be attracted to that. The negative part of water is oxygen. So the water molecules will flip themselves so that all the oxygens are facing the positive ion, are facing the metal. They'll all be orientated this way. Now, this attraction between the water molecule and the sodium ion is known as a molecule ion attraction. Okay? So the metal in the ionic compound is always positive, and it will always be surrounded by the oxygens. The nonmetal, which in this case was Cl minus, is negative, and water will orientate itself so the positive part of water is facing the negative ion. Again, because opposites attract. Okay? So the water molecules will surround those ions differently depending on what the charge is on the ion. If the charge is negative, H surrounds them. If the charge is positive on the ion, oxygen surrounds it. Do you see the difference? Okay? The water molecule flips depending on what the charge is on the ion. It's very important. I've actually seen questions on the Regents exam where they give you an ion and they ask you to draw the water surrounding it. So you have to know to turn the molecule the proper way, right? If the ion is positive, you surround it so that oxygen's attracting it. If the ion's negative, you surround it so hydrogen's attracting it. So the bottom line is, if we put it into words here, the positive ion on the metal is attracted to oxygen in water because oxygen in water has a partial negative charge. The negative ion in the salt is attracted to hydrogen in water because hydrogen in water has a partial positive charge. The bottom line is you're only going to get these molecule ion attractions when you take salt and dissolve it in water. So you need to be in the aqueous phase to have molecule ion attractions. You need to be dissolved in water. To have these IMFs. Otherwise you won't have them. Okay? And then, finally, our last and weakest, puniest type of IMF, IMF number 4, is called a, van der Waals force of attraction. It has a strong name, doesn't it? Van der Waals, but it's really weak. It's the weakest IMF there is. And van der Waals are attractions between nonpolar molecules. So some things that have van der Waals are like methane, like CH4, because that's the tetrahedral shape, which makes a nonpolar molecule. So CH4 has them. Carbon dioxide has them. Because remember, even though that has polar bonds, because of its linear shape, with more than 2 atoms, it's a nonpolar molecule. All your diatomics have them, right? Like hydrogen, chlorine, etc. They all have them because they're all nonpolar molecules. Even your noble gases have them, like krypton and xenon. They're considered nonpolar molecules because Lord knows they don't have charges. So they're considered nonpolar molecules, and they have these weak IMFs, van der Waals. Okay? Remember, a nonpolar molecule doesn't have any partial charges. So how do these come about? I mean, it's really easy to see how a plus is attracted to a minus, but how do these come about? Super abstract and confusing. But the way you get partial attractions between things that don't have charges is due to the movement of electrons. The electrons move about. And as they move about, they create momentary, weak partial charges, which can lead to attractions. These are the weakest. These are relatively weak. They are the weakest forces of attraction. But there are certain factors that affect their strength. First of all, size. The bigger the molecule, the stronger the van der Waals. And remember, if you have strong van der Waals or strong IMFs, you'll have a higher boiling point. So if we just compare a couple that we listed, who did we list? We listed hydrogen versus chlorine. Right? Hydrogen versus chlorine. They're both nonpolar molecules. They both have van der Waals. Who's bigger, hydrogen or chlorine? hydrogen only occupies one energy level, and chlorine is in the third row, so that it has 3 energy levels, right? So who's bigger? Chlorine is bigger, right? You can also do it based on the number of electrons. This has 2 electrons, because it's 2 H's each with 1. And then this has, what's its total? 17 and 17. This has 34 electrons total, and not just counting valence electrons here, I'm counting total. The bigger one always has more electrons, okay? So this has more electrons, okay? It's larger, so it will have stronger IMFs. This has stronger van der Waals. The bigger it is, the stronger the van der Waals. VD Waals is my van der Waals, okay? And the closer they are together, the stronger the van der Waals will be. So if you spread them out, if you move the chlorines really far away from each other, then they're not, the van der Waals forces are not very strong. They have to be close together to be strong. Okay? So 4 different IMFs that we know about, attractions between molecules. If they ask you for an attraction between molecules, there are 4. I'll list them. Right? You have your dipole-dipoles. Whoops. Those are between polar molecules. You have your hydrogen bonds, which are attractions between H and O, F and N. You have your molecule ion, and you have your van der Waals. Of these, hydrogen bonds are the strongest, and van der Waals are the weakest. Okay? Dipole, dipole, and molecular ion are somewhere in between. So things that have hydrogen bonds would have higher melting and boiling points for covalent things than things that don't. If they ask you, because that is actually a question that comes up often, they ask you who has the highest, I'm sorry, I lost the page. I'll put it back up in a minute. If they ask you who has the highest melting point or boiling point, the first thing you want to do is look for something ionic. Right? Metal to nonmetal have much higher melting and boiling points than anybody else. After that, you would look for just a metal by itself, right, with metallic bonds. After that, you'd look for something with hydrogen bonds, right, H with O, F, or N. After that, you look for dipole-dipole. And then finally, your last one is your van der Waals. They have the weakest IMFs. Paris? Yes. And when do I have to do that? Okay, thank you. All right, go ahead. And the last one is van der Waals. Okay? That's the weakest between nonpolar. Questions? I think we should try some of these on our own. So you have the sheet that you picked up when you came in, right? Let's do this. Kind of get together. So Rebecca, well, you know what? Alex, go sit with Rebecca, please. Let me pause this.